Hello, my name is Alan Retana. I am a master's student at INAOE and I am presenting the work titled Development of an Hydrogenated Amorphous Silicon Carbide-Based Biosensor for E.Coli Detection. Various types of pathogen detection systems have been developed in response to the urgent need to mitigate public health risks. The most commonly used detection methods are enzyme-linked immunoabsorbance assay and polymerase chain reaction assays. These are fast and reliable methods with low detection limits. However, their high costs, time-consuming nature, and specific requirements have led to the search for new detection mechanisms. Biosensors have emerged as new detection methods to complement the already used methods, as they are fast, easy to use, portable, and present high sensitivity for pathogen detection. Most biosensors can be classified as mechanical, optical, or electrochemical. Among these, electrochemical impedance biosensors that use interdigitated electrode arrays have gained attention. Over the past decade, there has been an increasing interest in exploring new material configurations to improve the sensitivity, the detection limit, to simplify the manufacturing process, and reduce the cost of these biosensors. In this work, the development of an hydrogenated amorphous silicon carbide-based electrochemical impedance biosensor for E.Coli detection is presented. The principal objectives of this work are to develop an E.Coli biosensor with accurate and reliable measurements, optimize the biofunctionalization methodology to ensure the results reproducibility, and to analyze the biosensor response by the change in electrochemical impedance as a function of bacteria concentration to characterize the biosensor detection limit. The methodology can be divided into two processes: the fabrication and characterization of the transducer, and the biofunctionalization and detection of bacteria. The manufacturing process of the transducer is as follows. Starting with a 2-inch silicon wafer, a thermal oxidation process is employed to grow a 250 nanometer silicon dioxide film. Subsequently, a 500 nanometer hydrogenated amorphous silicon carbide film is deposited by plasma-enhanced chemical vapor deposition. A photolithography step initiates the lift-off process. A 360 nanometers titanium layer is then deposited through evaporation. And after removing the photoresist, the interdigitated electrodes are defined with a separation and width of 20 micrometers. To characterize the transducer, impedance and phase measurements were conducted using a Hyoki IM3570 impedance analyzer across a frequency range of 10 Hz to 1 MHz. Applying an AC voltage of 5 volts. To obtain the biosensor, the transducer underwent a self-assembly monolayers methodology. This involves forming OH groups on the silicon carbide surface using potassium hydroxide, followed by exposing the device to 3-aminopropyl trimethoxysilane to generate aldehyde groups. Specific E.Coli antibodies are then absorbed onto the surface. To characterize the biosensor's detection limit, different E.Coli concentrations ranging from 1 CFU per milliliter to 10 to the power of 8 CFU per milliliter were used. Impedance and phase measurements were conducted with a drop of phosphate buffer saline over the interdigitated electrodes as shown in the figure. The results obtained in this section illustrates the average behavior of the fabricated transducer compared to a simulation conducted using COMSOL multiphysics software. As demonstrated, the simulation, represented by red curves, shows an ideal capacitor behavior, while experimental results, represented by black curves, exhibit real capacitor behavior with parasitic effects at high frequencies. However, at low and mid frequencies, simulation and experimental behavior align, indicating proper transducer functionality. The standard deviations, indicated by blue shadows, maintain relative low values, reflecting the reproducibility of the manufacturing process. Subsequently, the graphs present the detection experiment outcomes. The left graph depicts frequency versus impedance magnitude, while the right graph illustrates frequency against phase. As observed, The phase of most of the samples exhibits a similar behavior, indicating a consistent biosensor effect across all samples. Impedance curves follow similar paths, but magnitudes at low frequencies differ, implying the biosensors effectively detects bacterial presence by altering impedance values. The final graph shows impedance values of the sample at 700 Hz. Notably, there is no linear trend in impedance on 1 CFU per milliliter to 10 to the power of 8 CFU per milliliter, suggesting the biosensor lacks an obvious sensitivity value. However, it is evident that the biosensor distinguishes between bacterial presence and absence, with blank sample pairs consistently remaining below others, thus establishing a detection limit at 1 CFU per milliliter. The biosensor manufacturing process proved a high reproducibility and good agreement with the simulation results obtained by Thomson multiphysics software. With the EIS study, it was shown the capability of the biosensor to discriminate between the presence or absence of bacteria in the medium. Moreover, the biosensor was able to detect both low and high E.Coli concentrations. It is expected that with future work, this hydrogenated amorphous silicon carbide-based biosensor will be a reliable and rapid method for pathogen detection. Thank you.